Hi guys, welcome back to Data Every Day. Today we're looking at a data set of, well, it's a image set of Lyme disease rashes. So we're going to try to predict whether a rash is Lyme disease or not. So if we look at the images, you can see these are all examples of rashes that are not Lyme disease. I'm sorry for the graphic images here. Over here, these would be Lyme disease images. So let's hop into the notebook. We're going to try to classify whether a given image is Lyme disease or not. And you can see I have a task for today. Given images of various rashes, let's try to predict if a given rash is a symptom of Lyme disease. And we'll be using a TensorFlow convolutional neural network to make our predictions. So we actually only use 4 imports today. So I'm going to go ahead and import those. And let's take a look at some of our data to start. We want to get a sort of a sense of what we're working with. Even though we saw it on Kaggle, I'd like to actually run some code that will allow us to visualize the images. So whenever we're working with image data, it's usually stored in such a way that we have a folder for each class, right? So we're not using these by disease folders. We're using the train and validation folders here. And the validation folder is actually going to be our test folder, and we're going to draw cross-validation examples from our train folder. So if we go ahead and grab the file path for this directory, we can call it train directory, traindir, just going to be that path, and we can get the validation, no, this one right here, validation file path. We'll call it tester. We'll call it valdir because it's called that. Looks like this. All those are our strings. But if we then use TensorFlow's tf.keras.preprocessing.image dataset from directory. This will create a dataset that pairs examples with their labels automatically given a file path. So what it will do is actually use the name of the folder as the class name, and that's the standard way of formatting the data. You can change that, but by default that's the way it chooses the labels. So everything in this folder will have the class name Lyme negative, and everything in this will have the class name Lyme positive. So we'll go ahead and load in the file path, which was just traindir, and that will take these two folders and use them as classes. And we're going to give it a validation split. And it's important that here we use a random seed. Let's use 42. Just because we want to create two sets of data from the same directory, and if we're going to split it, we have to make sure we're splitting it in the same way for both of those data sets. So we use a random seed that will make sure that the random split is the same every time as long as the seed is the same. And this subset, this will be the training subset of the validation split. So when we use validation split, this is saying use 20% of the data as validation data. Then if the subset is training, it'll use the 80% that is not validation data, and if the subset is validation, it'll use the 20% that is validation data. Then we will specify a batch size, and I'm going to leave that for a second, and an image size, which I'm also going to leave because I want to declare it up here. Batch size, we want this to be the same across all the data sets, so let's make it 32. Sounds good. And then we're also going to have an image height and image width. Whoops, what did I just do? And let's make it 128 by 128. This can be any number of things. I believe the images are all of different size, so we're going to have to resize them using this. This function will resize them for us. So 128 by, this should be width, sorry, 128. the smaller the images are, the less data we'll actually have as input features, but the faster our model will train. So it's sort of a trade-off how you like to do that. For our purposes, since I don't want to make this take forever, I think 128 is a pretty good number. I'm actually going to turn on GPU acceleration before we go any further, because GPU acceleration severely increases the speed at which we can train convolutional neural networks. Of all the models, neural networks are the most affected by using GPUs, and convolutional neural networks especially. So the batch size here is going to be batch size that we just declared, right? 32. And the image size is going to be image height by image width. Alright, and this will create a dataset, which we'll call train DS, train dataset, from this folder. Now we're going to do the same thing right here, but this is going to be the validation data. So we'll call it val_ds. And we want to make sure we're using train directory still, because like I said, this val directory is actually going to be the test directory. So we're still using train directory, but we have to make sure that the subset is validation. And now you see why we use the same seed. So we want to make sure we're taking the same, like from the same split, Alright. And everything looks good. Then, oh wait, yeah, right. And then we're doing one more. This will be the test DS. This is what we'll test our model on when we're all done. This will draw from the validation directory. So right here. We're not using a split here. Right? And we're not using any of this. This is just straight up from the folder. Alright, so I'll run all these. And it should tell us how many files I found. If you didn't know, today's International Coffee Day, so enjoying that iced coffee. And we have, alright, 357 files belonging to 2 classes, and you can see it did this both once for the trained dataset, once for the validation dataset, because we're drawing from the same folder. However, for the trained dataset, it's only using the 80%, and for the validation dataset, it's only using the 20%, right? And then for the test dataset, it's using all 87 that are found in this folder. Alright, so let's just create, let's look at the class names that we're dealing with, just to confirm what I was saying before. So we'll call class names trainds.classnames. It's just the attribute that comes along with it. And we'll print it out to see what we got. And sure enough, it's used the folders as the labels. So Lyme negative and Lyme positive are our classes. So we'll be trying to classify images into one of these 2 categories. Alright, now I think we're ready to visualize our data a little. And I'm going to use matplotlib for this. So let's make a new figure. Give it a fixed size of 10 by 10. And we're going to display 9 images in a 3 by 3 grid. So note that if we let's say, alright, if I take, let's look at this, 4 images, images labels in trainds.take1 print images.shape. Alright, so you can see this function up here has already split the data into batches. So take 1 is saying take 1 batch from right off the top of our trained dataset. And you can see that it looks like it's iterating through, but this is actually just one set of images and labels. And here we have 32 images in the batch, each which is 128 by 128 by 3 for 3 color channels, RGB. So we're dealing with a set of 32 128 by 128 images, each with 3 color channels. And so what we're going to do is take that set and plot 9 of them, the first 9 of them. So for images labels in trainds.take1, and we will, here if I show you labels, it's actually the corresponding label for each of the 32 images, right? So this is a tensor containing all of the labels for each one, and this is the actual data, but there's only 32 elements in each of these. And when we iterate through take1, we're actually just getting one thing, which is the batch. And if I notice, we have class names, right? If I do class names sublabels, oh, actually that won't work. I have to get a certain one. For example, how do I do this? 0. You can see this is the 0th label. If I wanted to see what name that is, I can just do class names evaluated at the 0th label, which would be Lyme positive. Because I guess 0 goes to Lyme positive, 1 goes to Lyme negative, which is fine. It doesn't really matter. But with this, we can now create our plot here. So we're going to take the batch, and then for the first 9 images, for I in range 9, we're going to make a subplot in a 3x3 grid, and we're going to index starting with 1. Subplot requires that the index is greater than 0. Then we'll use the image show or imShow function from pyplot to, we're going to get one image, and this is really just a tensor of pixel data in a 128 by 128 by 3 tensor, right? We're going to turn it into a NumPy array, and then we're going to turn it into unsigned 8-bit integers. And we will then add a title, which will be like I did before, the class names indexed at the label of that particular image. So it'll give us the actual class name right above the image, which is what we want. And we'll just turn off the axis so it's unnecessary. Alright, and we'll show it for each after the subplots are all complete, and let's see what we get. Oh, this should be, wait, what? Oh, I misspelled this. uint. There we go. Alright, and sort of gross, but we notice this is actually a very sloppy data set, right? We have stuff in here that's not very well cleaned. So some of these are real rash data, but we also have like diagrams which aren't even real people, and yeah, there's text on this one. So we're going to see how our model does, but I'm not expecting very high performance. If we had more time, we could probably go through and clean the whole data set, get much better examples, probably improving our accuracy, but for our purposes, we're just going to try to do the best with what we have. And yeah, let's go. So basically, we are done visualizing, and we'll go on to, I guess we could say pre-processing, although we were already doing some of that earlier. We're going to cache our data sets, shuffle them. Actually, we're just going to shuffle the training set so that we get another element of randomness, and then we're going to prefetch the data sets, which will just increase the computational efficiency of our training. So before I start, I'm going to create this auto-tune variable, which is comes from tf.data.experimental, and basically this is a clever way of TensorFlow allows you to evaluate a sort of plug in a value dynamically at runtime. So I'll show you where I'm using it. We're going to cache this, So we're going to store images in memory so that we don't have to keep loading them up from the disk every time that we train for each epoch. And then we'll shuffle the dataset. We're giving it a buffer size of 1,000 here, and then we're going to prefetch the dataset. And this will allow us to process certain images while storing others in memory. So it's like preparing. It's like putting them in a buffer while we're doing one thing. We're doing that simultaneously, and we're giving it a buffer size of auto-tune. So it's going to like dynamically choose this value while it's doing it. And we're going to do the same thing for validation set, validation DS, except we're not going to shuffle it. And for test DS as well, but we're not going to shuffle it. Alright, and then we're just going to I guess start modeling. I don't see the reason of putting this in its own thing. Let's just say modeling. This can be included. Alright, so we'll start setting up our model. And this is going to be I think 2 convolutional layer CNN, since it's a pretty small data set. And yeah, I mean, I was experimenting before, and when we had 3 layers, it was, I think it was underfitting. So let's continue. So I'm doing an input layer, and the shape is going to be image height by image width by 3. So this is the size of our input. It's going to be 128 by 128 by 3, and we've set these up here, right? And then we're going to have a rescaling layer to start. So this is just going to normalize our data. We're going to set all the values between 0 and 1 instead of between 0 and 255. Sorry, what is scalar? I'm not doing that. tf.keras.layers.rescaling. No, actually it's experimental .preprocessing .rescaling. And the factor by which we'd like to rescale is 1 over 255. And we'll pass in inputs. Then we'll start with the convolutional layers. tf.keras.layers.conv2d. We're going to give it a filter size of 16, a kernel size of 3, and we'll keep same padding and give it a ReLU activation. Here we'll pass in x. And after that we're going to max pool. So tf.keras.layers.maxpooling2d, and we'll pass in x. And we're going to repeat this twice, like this, except we're going to increase the filter size here to 32. So we're getting a larger amount of the image each time. And we're not going to do a third one, but after that we're going to flatten the image, so turn it into a one-dimensional array of pixel data. tf.keras.layers.flatten, and then we will finish with a fully connected layer at the end with 128 activations from the ReLU activation function. Alright, and then for our output layer, this will just be our classification layer, which will be another dense layer, but we will give it only one activation. Well, this is just going to be the probability estimate of the positive class. So, which implies the probability estimate of the negative class. This one gets a sigmoid activation. And then we'll create our model, call it model, tf.keras.model, passing in the inputs and the outputs. And we'll compile it. We'll use an atom optimizer, binary cross entropy as the loss function. And for the metrics, I'm going to use both accuracy and AUC, area under the receiver operating characteristic curve. tf.keras.metrics.auc. We'll name it AUC. Alright, then we are ready to train. So we'll start with the number of epochs. Let's start with 100. And we'll fit it, history.fit. This time we're going to pass in our train data set. And we'll give it a validation data set as well. So validation data equals valds. And the batch size we already have. And the epochs we already have right here. Alright. And let's see how that goes. Oh, what happened? Oh, what is wrong with me? History equals model.fit. There we go. We have GPU acceleration on. Okay. Good to go. Whoa. What? Very interesting. We have, it says we're getting a validation accuracy of 100%, which I did not get before. Let's see, we're gonna see how this looks. Let's plot it. Alright. So, results, we'll say. Okay, we're gonna plot a new figure. And this will have a fig size of 20 by 10. I want a big one here. I'm going to put two plots next to each other. Basically, we're going to make an x-axis, which is just going to be a range of the epochs that we trained for. Epochs range will be a range from 1 to the number of epochs plus 1. Because, right, this won't be included in the range. So we have to put plus 1 there. And then on the y-axis, I'm going to have 4 different values, 2 for each plot. Train loss, val loss, train AUC, and val AUC. And so for the train loss, it's just going to be history.history sub loss. History is this model history, right? So it's all these. And loss will just be this one right here. And then for val loss will just be this, but val loss. This one will just be AUC, and this one will be val AUC. Alright, we have our axes. Now we're going to make two subplots. One for the loss graph and one for the AUC graph. So plt.subplot, and we're going to make it in a 1x2 grid, 1 row, 2 columns. And this will be the first one, and we'll plot epochs range on the x-axis and train loss on the y. We'll label that training loss. This one will just be validation loss. So this will be val loss. Alright. And then we'll give it some labels. So X label will be epoch, and the Y label will be loss. And we'll give it a title as well, training and validation loss. And let's just show the legend. Alright, now I'm going to copy this and make a second subplot, which this will be the second one. And this is AUC, 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 and this is AUC. Alright, and then we're just going to show. And very interesting. Something sort of suspicious about this. They're going down at exactly the same time, so I just want to make sure that I didn't accidentally load this in the wrong way. Let me see. Just want to make sure. The only thing is I switched those. Whoops. Right. Okay. Let me try running it again. We should be okay. It's just when I was training it before, I did not get this kind of 100% validation accuracy. But I guess a good way of figuring it out is let's just evaluate it on the test set, and if we really do have 100% accuracy on the test set, then we know nothing went wrong. So this is on the test df. Alright, so it's done. Test df is ds, sorry. And apparently we classified every one of them correctly, which a bit of a head scratcher. I was having a very hard time doing this earlier. Hold on, I'm going to take 1 second, try to figure out what the problem is, and I'll get right back to you. Okay guys, I figured out what the problem was. I'm sure you may have caught me doing this, but I knew something was wrong. There's no way we're getting 100% accuracy. Over here, I've actually overwritten the val ds and the test ds as the train ds. I forgot to change these. So this should be val and this should be test. Now we should have an actual model that is doing something wrong, which is a good thing. Always be suspicious if you get 100% accuracy on your first try. And that's much more like what we're looking for. And it's actually not so bad considering the data set that we have. 0.7 or above is really good. If I can get over 0.75, I'm going to be happy here. So let's see. Okay, this is a much better set. However, you can see that we're overfitting the data. And usually what I do is I just do what's called early stopping, which is I just stop right here when the validation says lowest. But James Paladin pointed out in the comments, thank you James, that I should focus on some alternate ways to reduce overfitting and to improve model performance. So I'm going to try improving the model architecture here to try to get a better AUC. And you can see that we actually have an AUC of 0.7. So let's try to get that up to something higher. And there's a few ways to do this. First, let's see if we can sort of stabilize the curves here. So you can see it's very jagged. There's a lot of noise here. One thing that helps a lot with this and can overall just increase performance is by adding batch normalization layers after the convolutional layers. So we'll add here batch normalization, and the we're trying to beat 0.7, remember. Okay, so batch normalization, passing in x, and we're just going to put that after each max pooling layer. I was doing some research. Apparently, whether you put this before or after max pooling really doesn't matter too much. But it seems to be the best to use this after an activation. Alright, so let's just train that again and see how that goes. To see if that will smooth our curves out so we get more sort of stable results. And is this it? Yeah, you see it has really improved this sort of stability of the model, because every time it passes it into a new convolutional layer, it centers the data at 0 and gives it univariance. And does that across the whole batch. So neuron by neuron, it's going to normalize those values. So that each element, each image in the batch is on the same scale as the other images. There's also layer normalization, where each image gets normalized, but we're not doing that. We're doing batch normalization, and now let's see what we get. So let's just note our baseline. I'll put this in a markdown, is going to be this value here. Let's evaluate now, and we get 0.73. However, I'd like to see what early stopping gives us, because now we actually have a smoother curve, so I'm going to stop it right around here. We can actually notice something here. It's very interesting. I'm going to get the argmin of the validation loss, which is just going to be the epoch at which we have the lowest validation loss on this orange curve here. And actually, why don't I just add a little color over here so we can distinguish these. So color here will be blue, color here will be red. So looks like that. If I get the minimum argument, or the minimum x coordinate, that gives us the lowest y in val loss, it's epoch 9. So right around here. However, if I get the argmax of the val AUC, which would be the maximum of this red curve, we actually get 44. So what's that saying is that our performance, our model performance, is still going up while our loss is going up. And that can happen for various reasons, but the most, what it's really saying is that our model is getting better at generalizing to new unseen examples, while at the same time performing worse on the images that it's unsure about. So you can see, because it's binary classification, you can say an image is positive or negative, but let's say it makes a mistake, right? If it makes an incorrect guess, there's a difference between being slightly unsure about it and being really unsure about it, and that's what the loss is reflecting. A really high loss means we're just getting way off base, but the classification is still just binary, right? So this is like it's sort of like a confidence estimate. And if it's getting really confident about an incorrect guess, the loss is going to go up. However, at the same time, we're getting better at making correct classifications across the whole data set. And so that's what this is reflecting. So this is really what we want to maximize. The loss is not really what we're interested in. We want the overall performance, and AUC is a much better indicator of performance than loss is. So we're going to actually stop it at around 44. And so we'll change epochs to 44, or I'll do 45, and we'll retrain. And then we will see what we get as our okay, so this is interesting. It did not do so well. Let me try doing it once more. I feel like there's an element of randomness or stochasticity here. This time it looks like it's doing better, but we're still getting about 0.7. Right. So, wow. This time we got 0.8. Fishy, right? I mean, we could say, call it quits, that's 0.8, but if we're getting very different results per run of the model, then we probably need to try to run it a few times to get a sense of how it's doing. And now it's down to 0.62, so this is not working so well. What can we do now? Well, let's see. What can we do? There is something else I would suggest. Let's add a callback function to the training over here. So callbacks is going to be tf.keras.callbacks, and we're going to use a callback called reduce learning rate on plateau. And what this will do is, when it sees that the loss is starting to plateau, it's going to reduce the learning rate so that we can converge more nicely, and it will be less stochastic and much more like smooth convergence. We can also try training for a higher epochs to see how that goes. We'll reduce it again when we see where the dip is. So let's run that. And you can see it should be converging more nicely in the validation accuracy. So let's see this when we're done. Alright, now we have a very nice smooth curve. Alright. However, we're seeing the same sort of thing going on, where the loss is going up, but the AUC is also going up. So let's see what the argmin and argmax here. Argmax here is 73, around here. So if we evaluate now, we get something that's 0.718. I just want to see something. See if there's anything else we can do here. Now we could a good thing to do here would be to use k-folds cross-validation, which would be to basically train. Well, you pick a number of folds, say 5. You train 5 different versions of the same model, but each time you'd split the data into 5 sections, and each time you train the model, you use a different one of those sections as the validation data. Now, I'm not going to do that because it takes a bit of time and effort, but I will definitely include it in a future video, and that will give us a more stable result regarding the performance of our model. But I think for now this is all right. I mean, I experimented with some new techniques. Let's try it just one more time. We're going to stop this around 45 epochs, and then, which seemed across all the training, this was the most stable number of epochs, and see how we do at the end of that. So it looks like this is coming up to a maximum here, which looks good, and then we will evaluate it, and we end with 0.69. So not much improvement. I was able to get 0.78, but what's that really saying? I mean, we got 0.82 and then 0.62 the next time. So yeah, overall I'd say we're able to classify Lyme disease with reasonable accuracy. Now, a way to take this really up to the next level would probably be one, to clean the data set, or to use a pre-trained model like ResNet or Inception or something that is already really good at classifying images, which then we can just append a little trainable part on the end that will generalize to this example of classifying Lyme disease photos. So I think that sums up today's video. I hope you liked it. If you did, make sure to subscribe and hit the bell and leave any comments in the section below. Thank you so much for watching, and have an absolutely fantastic day. See you guys tomorrow.